What we're doing now, remember now, we've gone through the calculations, and you did in your homework basically calculating those forces somewhere on the interior of that beam. So we've looked at that concentrated couple or moment, shear force, which now is going to be perpendicular to the axis of that particular member, and then axial force if there happens to be any. Now, most beams are going to be flat, so we're not going to really be looking at axial forces and stuff. But this is basically going to be our starting point. And what we're going to be doing is creating shear and moment diagrams. And what shear and moment diagrams are very just nice ways for a designer to look at and say, I need to design for this much moment. I need to design for this much shear. And what we see is that it varies as we go across the beam. So we may not need to design for as much moment here as we would in the middle. And shear might be higher, and usually is, around supports because of those concentrated forces. So what we're going to be putting together is these shear moment diagrams, and there's a sets of rules that we kind of have to follow. And the first one was what is considered positive. And we'll put those up again. Let's see, up, down, and our bowl. So clockwise and bowl. If you ever forget them, that's an easy way to remember it. But basically, those are going to be our rules for creating these diagrams. Now, the funny thing is then when we have a positive moment, and we have a positive moment diagram, then it depends on whether you're designing reinforced concrete or steel, because they'll show it on the opposite side. Concrete likes to show positive moment on the bottom because that's where you put the steel. So it's a visual aid to the engineer or the designer, basically, to say, oh, I've got positive moment there. I need to put steel in the bottom of it. It's just the opposite in steel. If you have positive moment in the middle of the beam there, they're going to show it on the top side because you have compression buckling of the top flange that you have to worry about. So you basically have to beef that up somehow. So where you put it doesn't matter, but the positive and negative connotations basically are going to be the same. Now, a couple of things. What we're doing now is we're going to do this method of sections, or the other way it's known as the equilibrium method, because what we're going to be doing is a bunch of free body diagrams and equilibrium problems. And we need to think about where we're going to be doing those. And when we look at our beam here, again, the best way to look at a problem like this is look at it in terms of the free body diagram, because notice this isn't a roller, this is a force. This isn't a pin, this is a force. And you need to think about things in terms of forces and couples when you go across there. Now, we're going to be making cuts, and there's the first cut that we, I think, started talking about on Thursday was there between 0 and 10 feet. And what we're saying is then I know what's going on between 0 and 10 here. My uniform load there is going to be uniform wherever I cut it, at 1, 2, 5. But I can do a little calculation. It's going to simply be 2 times whatever that distance is to give me that value there. So I know that I can make a cut anywhere in here. And as long as I express my load in terms of that x value, which we did, then basically everything's valid between 0 and 10. Now note, when we get to B, our uniform load disappears. Okay? So we're going to have to make another cut. So we're going to make a cut somewhere in here that's valid between 0 and 10. The next place we'll make a cut is between B and C there. Nothing's going on between at the 11 feet, 12 feet, 13 feet. We're moving away, but basically our uniform load disappeared, and we also have this surprise concentrated load of 10 kips. So now all of a sudden it's going to show up. We'll make a cut along here, and then notice when I pass point C, all of a sudden now my free body diagram is going to include this concentrated twist of 500 or 50 kips per feet. So I'm going to have to make another cut out here and incorporate that particular load into my calculations. So when you draw your free body diagram, the first thing we're going to be doing on almost every one of these problems is coming up with our support reactions. Once we get our support reactions, again, think of them in terms of forces. Look at your free body diagram and say, I need to make 3 cuts in this particular case. Now, one mistake everybody tends to make, and I want you to be careful of, remember when we did this calculation for the support forces, we put in a concentrated load, right? An equivalent load. Okay, that's just simply a manifestation. That's an equivalent load to give us the tools to use our equilibrium equations to solve for the support forces. Our beam does not have a concentrated load there. It's a uniform load. So we create equivalent loads to help us use our calculations, but that is not the load on the beam. And we're going to see that when we look at shear and moment diagrams for areas where there's uniform loads and areas when there's no loads or concentrated loads. And how far did we cover the first one, section A to B? Well, we'll do it again. Now, one thing we also have to be careful of is what span these equations are valid over. So we're doing this particular section from A to B, which is from 0 to 10. And again, what we're going to be doing is free body diagrams and equilibrium equations. Very simple, not too horribly complicated. It's just how we apply them. So we're going to look, and that's our very end of the beam. That was that concentrated reaction force that's necessary to keep the whole beam in equilibrium. It doesn't change. We'll put in our positive convention for shear and moment. If they solve negative, we'll show them as negative, but right now that's the positive convention. And then our load is going to be here. Now again, it's a distributed load, so it's to be changing. But what we're going to be doing is just simply substituting in a calculation for that equivalent load, which will be 2x, and we don't have x up there yet. So that's the equilibrium problem. Nothing to it. Then we set up our equilibrium equations, the two equations that we'll be most concerned with.
Isn't there the concentrated force too? 10?
Well, but notice I'm just short of 10. Okay, so that's a good point. That's a very good point. These equations are not valid under a concentrated load or a concentrated twist. So we have to be a little careful. What we're going to do is go right up to that point, and then we're going to jump across it and make a cut there. And we'll see what happens. But good point. So there's no concentrated load at this point. We have an equivalent load here of 2x. And then we'll set up our equilibrium equation. The 17.5 is acting up. The minus 2x is acting down. And my shear positive convention is down, the way I've got it set up in terms of my equilibrium equation. So again, remember, this is just a mapping. I set up my coordinate system the way I want in terms of that. And what we find then is we get an equation now that expresses how that shear changes, which makes sense. When we think about it, it's going to start off at 17.5. And then as I move along there, the distributed load is going to be subtracting away from it. So as I add more and more distributed load, what we're going to see is that start to disappear. Do the same thing with our moment.
was the moment force 2x? Why was that 2x?
Because it was 2 kips per foot, right?
Oh, okay.
Yeah.
There you go.
And x is measured in feet. Yeah, yeah. OK, so we got that. And then we're also going to take our moment. And I suggest you can take moment anywhere. You'll get the same equation wherever you take it. It's generally easier to take it at point x because then the shear doesn't come into it. If I did it over here, which is fine, then I better make sure my calculation for shear is correct because that's going to enter the moment equation there. So generally we take it there, but again, moments have to be equal to 0 everywhere. You can take it wherever you want. In this particular case, we have the 17.5, and notice that it's got a moment arm now of the x. The other force now, and that's, again, going to be based upon my twist. That's going to be twisting now opposite of my right-hand rule there, so I show it as a negative. My r will now be providing force in the opposite sense, so I've got the plus 2x. And what's the moment arm to that? I'm here, and it's going to be acting through the centroid of a rectangular area, x over 2. And then don't forget our variable m, and that's shown in a positive sense there. So when I get done with that, I plug in. And what I find now is my moment is going to be a parabolic equation, which kind of makes sense. Now, when we look at the piece there, notice the 17.5x is x. So yeah, as I move along there, my moment arm grows by x. But this one's a little bit different because it's moving, but its center is moving also with x, too. So it's going to be changing, and that's where we end up with the x squared piece there. And then our boundary conditions for this, x equal to 0, v equals 17.5. And when we plug that into the moment equation, it's equal to 0. And then my far end, x equal to 10. And we find the shear is equal to a minus 2.5 when I plug it in of 10 there, and then the moment will be 75. From point B to point C is what I'm doing. So, and then I'm also putting the range here. So either one you can use, but from point, so I'm going to be making a cut now between B and C. Because at B, things change. My uniform load disappears, and I see this new concentrated load show up. Nothing happens on that section until I get out to C, and then C, all of a sudden, that concentrated twist shows up. So what I'm going to do is a free body diagram appropriate to that range. My concentrated load at the end there doesn't change. Now the interesting thing is now when I get to 10, my uniform load ends, so my R doesn't change anymore. That is equal to 20, right? So I've gone past my that uniform load there, so R doesn't change anymore. The equivalent load is going to be now 20, and it will be acting at 5 feet. So that doesn't change anymore.
AC, not BC? Because if that's BC, there's no...
Oh, well, I'm making my cut in BC is what I'm implying here. But yes, what we're doing is from A to C.
Okay.
Yeah, so make a little note to that effect there. Sorry about that. What I was trying to imply here is where I'm making the cut, what the range is. And it's going to be important because when we start doing these equations, we can't be using this equation for 15 or 20. It's only valid between 0 and 10. This one's only going to be valid between 10 and 15. So that's the key thing I'm trying to indicate there. Okay, so we got our shear and our moment. And then the other thing we've got here, I forgot to put on there, is that 10 kip load. So we got that concentrated load. So all of a sudden it shows up, and I'm going to have to account for that now in terms of my equilibrium equations. Okay, so I've got my 17.5. Now when I consider that uniform load, now again I'm using my equivalent load, it doesn't change. So I'm going to now have a minus 20. And then in addition to that, I've got that concentrated load, which now shows up. So I have to account for all of those forces now that all of a sudden appear on this free body diagram. And what this tells me now is that the shear doesn't change. It's going to be a fixed number, which makes sense. Let's think about that. Shear is just simply going to be vertical equilibrium, right? So as I'm cutting from this point on, there's nothing going on. I'm not adding load. There's no uniform load being added or a triangular load or anything like that. I'm not doing anything until there's another concentrated twist or load or something like that. So basically, it does make sense that my shear isn't changing. This is fixed. This is fixed. Concentrated load there is fixed. So when we're cutting through an area where there's no load showing up, we should expect to see a shear not changing, a constant shear. Now moment, unfortunately, moment arms change. So we still got that piece there. And we'll notice that some of these pieces are going to just be carrying over. They're going to continue to show up there. So my concentrated support force there, 17.5, is going to continue to be x away. We didn't get our x on here. And then the other piece that we got is this 20 kip load, which we determined was going to be positive. How far away is it acting? X minus 5. Cool. I'm going to make mathematicians out of you yet. OK. Then we've got this 10 kip load, which is going to be acting in a positive sense. How far away is it? X minus 10. Cool. Plus m. We don't forget our variable there. And when we plug in all of those values, what we get now is a moment diagram that's going to be changing linearly. Which again makes sense because all of these loads now, even in the equivalent load, are all in fixed locations. The only thing changing is my moment arm. So I should expect to see my moment changing by some sort of a linear value there, with the starting point there too, but that's the y-intercept, and we don't care about that because it's not valid for the equation. And then what we're going to do is look at our boundary conditions again for this. Question?
In different kinds of scenarios where the distributed load is irregular, so it's not linear, it's not any known relationship, it's not parabolic, it's not exponential. How will we try to analyze that? How will we analyze the system?
Well, usually, and you'll see this in EIT exams and stuff like that, they'll give you a load with respect to x. You'll probably see like linear loads. There might even be a parabolic load and stuff like that, but it'll always be some relationship to x. You have to get it into a relationship of x. So that's your first assignment. If it isn't, then what you're going to have to do is break it up into little segments and little pieces like that and do it that way. Yeah. Yeah, step crossed it. But that's what we're kind of doing when you think about it here, is that we're kind of, that 10 kip load we don't know. Is a concentrated load the vector, we would have to go into higher mathematics. What we do is we just simply trick it by cutting on this side and then cutting on that side. And what we'll see in the diagram, I'll explain to you why it looks like it does. But we'll see a jump basically in our diagram. But let's finish up here then. Boundary conditions, and if you want to call it 10 plus, push that a little too much there. Okay, so just past that 10 there, what we find is then our shear changes from 2.5 to 12.5, and our moment stays the same though. It's 75 here, and it's 75 here. And again, let's think about that. What does that mean? Well, when I start thinking about my moment diagram, well, first of all, when I think about my shear diagram, as I move across this little point here, all of a sudden I have 10 kips showing up as a concentrated load. So instead of going with a stepwise function and that sort of thing, I just simply include it into my equation, and I'm going to draw a jump in my diagram there. So I'm going to jump from 2.5 to 12.5. Which is, we'll see how that looks in the diagram. But again, what we're trying to do is get this information to a designer to say, OK, I need to put more steel in there. Question?
I guess the question I was asking earlier was, what does the lowercase bc mean?
Oh, no, I'm sorry. That's kind of boundary conditions or the boundaries. What we're doing is getting the two endpoints. Actually, maybe let's put it, that's a better way of putting it. Let's put it endpoints. Because what we're going to do is we've got to draw this diagram. So I'm just trying to get my endpoints there. But it also helps us when we're drawing this because let's go to the moment diagram. It's 75 here and 75 here. Well, let's think about in terms of concentrated twist as I go across this point there of that 10. Well, yeah, the 10 kip load shows up, but I have virtually no moment arm there, right? So I shouldn't expect to see any sort of jump in my moment diagram due to a concentrated load because it starts off small. Now, yeah, it'll start picking up as I move away, but when I make a cut very close to that 10-foot level there, what we're going to see then is that the moment shouldn't change. And in terms of the beam, that makes sense. It's a continuous beam, so we're not going to see any sort of changes there. Moment's basically describing how it deflects and that sort of thing, and we're not going to see any kinks there. So that makes sense, and then what we'll want to do is take it to x15 and just short of that. And what we see is, again, the shear doesn't change, which makes sense. Nothing's happening across there. But the moment does. And it goes from 75 to 12.5. And again, thinking what's going on there, this 17.5 was really driving my twist in the one direction. As I start moving along there, these two start having greater moment on it, so they're going to start wanting to twist it back in the other direction there. So the moment's getting a little bit smaller as we go along there. So to go with your convention there, we're going to draw now a free body diagram past that C. So as you can see, this is kind of rote. This is going to be like a method of joints and trusses and that sort of thing. In terms of this equilibrium approach, we're just going to be doing equilibrium body after equilibrium body. The key thing is what's happening is as we go from section to section there, we're including more forces in that free body diagram. So what we've done now is we've gone now past point C there, and all of a sudden this 50 kip twist shows up. Again, some of these dimensions haven't changed. So we're doing our x out to there, and all of those particular locations show up. And again, we just simply do equilibrium equations. So sum of forces in the y direction, again, we're going to include that concentrated load. We're going to include the equivalent load and the concentrated load. Okay, do I include this one? I see a couple of shaking heads, several.
This direction?
Huh? What we're doing is sum of forces in the y direction. We've just now gone past here. We're looking at this guy. Do we include this in our vertical equilibrium equation?
No.
It's not a force it's not a linear force. It's a twist. So basically, our shear. Yep. Is it 12, right? Sorry. Oh, that's right. The first one was 2.9. Okay, now, though, let's think about the moment equation. And again, note as we walk along there, we're just going to be carrying a lot of these same pieces. These haven't changed. All we're going to do now is pick up a concentrated twist. So concentrated support force looks the same. (20 minus x5, 10 x minus 10). That's a plus, so those haven't changed. Now we look at this one, and we're going to, because it is a concentrated twist, it's already in kip feet, so I really don't need the 15 feet here. I put it down there to see if I could draw your attention to it, but it's already in kip feet. Its twist is going to be positive or negative? Negative. And then I include my variable. So key thing with the concentrated twist, if you see one, it's already in moment form, length per weight or force. It doesn't matter where it is. The only key thing is does it show up on the free body diagram based upon where you cut it. When we cut it over here, it didn't show up. Once we got over here, it showed up in the cut. And it changes my moment equation by simply that concentrated twist. It's going to go from 200 to 250.
Is it 12.5x?
Yes. Thank you. Okay. Okay, so let's look at our various values here at the endpoints. So again, my shear doesn't change. It's going to be the same across there. And again, shear doesn't change there. When I plug in the new values for m, however, it's equal to 0. Does that make sense?
Yep.
Why?
There shouldn't be any moment on either side.
There shouldn't be any moment. You're right. There is a, what is it, a roller on that side or a pin? Okay. But there's nothing there to support any sort of concentrated twist, right? It's free to rotate. When we see that thing bending because of all those loads there, it's not going to resist rotation at all. It's going to allow it to rotate, which says then that I have no moment capacity there. I should have no moment. So again, we're beginning to see now how this moment is changing across there, and that's what the designer, that's what they're going to be looking at when they look at that moment diagram. Now, one quick little trick is notice as we keep going along here, we kind of get buried with all sorts of stuff. Although a lot of it's building on the same thing, we can also look at it in the other direction. And I'll call it DC, but what we'll do, I'm going to draw my pictures up here again. And the reason I want to draw this is now what I'm going to do is look at, this is point D here. What I find is that there's a concentrated force due to the reaction at that end of 12.5. Now, when I look at this free body diagram, none of these forces appear to it because I'm making a cut here and looking this way now. When I put in my positive quantities, which way should my positive direction for shear be when I make this cut? Up. Good. You guys remembered. We're going to use this side of the positive convention. So we're doing Newton's third law there. And the same thing with the moment. It's going to be a twist in the opposite sense. So again, that's just the positive quantities. If they solve as negative, we'll show them as negative. The only other tricky part then is we need to figure out what that distance is. And if we're doing it in terms of x for the rest of the thing there, we need to do it in terms of x for this portion. But that's pretty easy. What would it be? 20 minus x. So as I vary it x there all the way to 15, basically, or if I take it to 20, it'll take it to the other end there. Now let's just plug those into that equilibrium equation. As soon as I figure out where I put my pen. So that's my free body diagram of DC. So if I plug the two values in, they're both acting up, which then solves for the same value I got over here. And the moment one's going to be a little messier, but still doable. Now notice I've chosen my convention with the right-hand rule. The moment for positive convention there is going to be in the opposite sense there. So I show it as negative. And then the only other force I have to worry about is the 12.5. It'll be acting in a positive sense. And now it'll be, well, make sure I get that right. Like so. So I put in the proper x value there based upon the x that I used over here. When I plug that all in, magic. Same equation. So again, it's the same thing. There's only a little bit of trickery here in terms of getting the x value proper. But otherwise, it's actually a lot simpler free body diagram. And it's also a check. If you've gone this way and you've added all these things and all these terms, the possibility of a positive sign or a negative sign getting screwed up could mess up things. Do the opposite end. Take a look at it that way and see if you get the same equation.
question. before
Sure.
you answer it.
Okay.
Why doesn't the moment at the point, what is it, C, why doesn't it change with X, like when you're doing moment at X? And the sum of the moments at X, like why does it stay 50 regardless of the distance from point C?
This one? As I move along, again, it's a concentrated twist. So it doesn't depend upon any distance. Remember, that's that free couple. Remember way back when we were talking about free couples and free vectors and that sort of thing? That's what we call that. That's that free vector. What that means is then I just freely plug it into the equation. Because it doesn't matter whether I'm here or here or here. Basically, it's going to be the same twist to the body. Think of a car tire when you're putting you're taking the lug nuts off. If you use this lug nut or that lug nut, basically it's going to create the same twist on your tire. It doesn't matter because it sees it as a concentrated twist. So it's not a function of distance. And that's why I put the distance there, but it's already in terms of a moment there because it's in terms of force times distance. So we just freely plug it into that equation as a concentrated twist, and then it adds to our equilibrium equation there. Does that make sense? We can talk a little bit about it after class if you want. Well, okay, so that was that side. Okay, so we just put together a little table here just to talk about our various areas here, but so just the equation is this, and then my endpoint range is like that. So it's that minus 2x. So we're going to basically put them together. So the equation that's valid for this range then for the moment is going to be the minus x squared plus the 17.5x. Okay, so that's that range. And then the next one, the nice thing about that one is that's a real easy value. That covers my endpoint. So the equation is minus 12.5. The equation for moment and the two endpoints there are 75 and 12.5. Endpoints, yeah. So it's at 10 and then at 15. So it goes from 75 to 12.5. And when we look at it, let's look up here. That's a good point. It's going to be a linear change, right? When we look at this one, parabolic. So we're going to have to think about how we're going to draw that. And we'll talk about that in just a second. And then our final piece is CD. And again, that's a real easy one. The shear doesn't change in that range. My moment equation looks a little bit different, but we'll notice a couple of things here is that there is a jump in my moment diagram here because it ended at 12.5 in section BC, but when I start CD, it starts out at 62.5. What could that mean?
Isn't there minus 12.5x is a PD?
Oh, yeah.
Oh, thank you. My x's are disappearing on me. Okay, now one thing I want to bring up is we have one little issue with this equation here. Now, linear equations go from point to point. When things are constant, they stay constant. The problem with parabolics and cubics and any sort of value that we go beyond 2, exponent equal to 2, we have the ability of our equation to do something like that or something like that, right? So when I say my endpoints are 0 and 75, that doesn't necessarily mean that that's the highest moment. That's just simply my endpoints. So I need to take a look at that equation and figure out whether I have what we call a minimum, maximum, or a saddle point. You remember that? And how did we go about getting those? Calculus. Do we want to do calculus? How would I get it? Derivative, yeah. What I want is my slope equal to 0, right? So let's take that equation and do the derivative of that. I should make you come up and do that. So we just took the derivative of that, right? So I get a minus 2x, and then and I set that equal to 0. Does that look like anything?
Yeah.
Interesting. So the key thing now is though we'll set that equal to 0. And we need to solve for the x. And what we do with that is then that tells me that this min or max or saddle appears within the range of my equation, right? So that means it's going up and then coming back down, or it's going down and coming back up. So the way we figure that out is let's figure out what that maximum point is. We'll just simply plug in that into my moment equation. Where is it? And what I find is then I found a maximum at that point because it went up a little higher than either one of my endpoints there. It went up to 76, almost 77 kip feet. Now, a couple things it tells me is then when we go back to this equation, what that's telling me is then when the shear goes to 0, my moment either maxes out or it mins out. It changes slope. So in terms of finding the maximum moment, I always need to check on this portion to see whether that saddle or that min or max falls within this range. It happens in this case to fall in that range. If x was equal to 20, it's not valid because our equation is only valid for this. So when you plug it in and x comes out to some value that's not on that, then you don't worry about it. It's just moving up that way, but it's not flattening out. In this particular case, since it came out at 8.75, it went up, reached that, and then dropped back down to 7.5. And we'll draw the diagram. OK, so we've got each of those pieces there.
Wouldn't this make sense to look and see it's negative, so it has to be like that?
If you look at the constant in front of that, yeah. That's another way of looking at it. But that'll tell you whether I'm maxing or minning, that sort of thing. And if you do a cantilever, it'll be the opposite way. So our diagrams, then, this is where we're going with this whole thing. Did I do something wrong? No? Okay. Okay, I'm good. Good. Well, I'm glad. Okay, the way we draw our diagrams, the first thing we do is I draw our free body diagram. Now again, our free body diagram doesn't have an equivalent load. It has a uniform load, so we need to make sure we have that there. It does have a concentrated load there. And again, the reason we draw that free body diagram is, again, the designer needs to know, okay, this minimum or maximum or this high shear or low shear, that sort of thing, I need to know where it is in respect to basically the forces that are acting on that body. So the next piece we'll draw is in our shear diagram. And we'll choose another cool color here. We'll do it in blue. OK, so we talked about it. Our starting point was 17.5, right? And by the time it reaches that 10 there, it draws down to minus 2.5. And then I've got my equation that says it's linear. So I just simply plug that in, draw it. If you want to put it in Excel, you can do that. But when I look at my other piece there, I notice that my shear now is 12.5. This is the time where you go 10. Where did 10 come from? And then for the rest of the body, it's going to be minus 12.5 across there. Now let's think about what we're seeing here. OK. A jump in my shear diagram. Again, remember what shear is. It's just simply vertical equilibrium. So when I make a cut very short here, it's not going to see much distributed load. As a matter of fact, if I take it at just past the 0 point there, the only thing it sees is a 17.5. So yeah, it's going to start off with a big jump there. It goes from 0 to 17.5.
This is like an old math question. Are either one of those circles supposed to be like hollow and one's supposed to be filled in? Or are they both filled in? Does that make sense?
They're both filled in, but you can make them hollow, though. I won't take out points for hollow.
Like hollow means one of them, you know what I mean? Because like as it approaches it from one end and as it approaches it
Oh, yeah.
Okay, never mind.
Yeah, we could draw that. OK. When we get to this point there, so as we go across here, too, now we started off at 17.5, but notice in terms of my vertical equilibrium, as I move across there, that 2 kips per foot is increasing, 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 to the point where it actually drives me down below into the negative range, minus 2.5. And then when I jump just across that 10, there's that big 10 kip jump. Vertical equilibrium, well, I've got to account for it. So my shear diagram will show that. And then as I go across here, yeah, I have a concentrated twist, but that doesn't have anything to do with vertical equilibrium. It's happy, and it just keeps at that minus 12.5. The end point, minus 12.5. Look pretty familiar. Again, it's that jump. So think about when you draw your shear diagram, you always need to think about it in terms of the free body diagram. Think about it in terms of forces, not in terms of supports. And finally, we'll look at our moment diagram. Oh, let's do that one in green. OK, so it starts off. Well, maybe I won't. It starts off there at 0. And then when it gets to this point here, it's 75. But then we talked about that equilibrium point there, that point where shear is equal to 0. We've got this that parabolic diagram now going with a 0 slope at this point here. But the key thing is that my max now is at the 8.75. And as a designer, I need to know that, because if I'm going to be putting steel in reinforced concrete or beefing up my compression flange in my steel section there, I need to think about, okay, what's the highest? Do I need it everywhere? And that sort of thing. Okay, then as we look what's going on, it drops down to 12.5. Oh, the other thing we need to put up here. That's my equation. So again, if you want to plot it in Excel or something like that. The equation for this piece here I keep forgetting my X. Now again, you see that the y-intercept is 200. So if we extended this all the way basically to x equal to 0, it would be intercepting at 200. But it's only valid for this range here. And then we cross that concentrated twist. And my equation changes by that 50. And what we see then is a jump in the moment diagram when we cross this concentrated twist. And again, that makes sense when we think about it as we move along there. And again, we'll just talk about this as we move along there. So we start here. Notice that there's no concentrated twist here. It's not a frozen, it's a pin. So it's basically going to be free to deflect basically however my loads tell me it wants to move. So basically what it says is my moment is going to be equal to 0. As I'm moving along here, it starts going higher and higher and higher to a point here where now this distributed load is starting to take over and saying, I'm going to twist you in the opposite sense there. So I reach a max at 8.75, and then I start coming down to the 7.5. Then as I make a cut through this area here, nothing's going on in terms of load. No load's being added in that section there. So basically, my moment diagram's only a function of x, only a function of its moment arms. Move along there linearly, it's starting to come down, and then I make a jump. I cross that point C. There's a concentrated twist. My equilibrium equation says, OK, I've got to pick up that concentrated twist. The way I do it is in my diagram, like so. Do that little jump. And then basically, with the equation, plug in the values. It goes back to 0, again, at a pin or a roller connection there, because there's nothing restraining the rotation there. OK, so let's just make some notes here. Again, as we talked about that, we think about these not in terms of supports, but in terms of forces. If it was a fixed connection there would be a concentrated twist there too, which would show up in my moment diagram there. But again, anytime there's a support, we should expect to see a jump, whether the support's on the end or it's in the middle. Because again, what is support doing? We substitute it with a concentrated force. OK, so we notice that the jumps in the shear diagram are in the same direction as the concentrated force. The jump in this one is up. Jumping that one's down, jumping that one is up. Then conversely, basically, we need a concentrated force for a jump. So if you've got a jump in your diagram and you don't have a concentrated force there, go back and look at your equations. You've done something wrong. And again, going back to the fact that supports are concentrated forces. So the support could be out in the middle somewhere. Okay, moment diagrams are generally continuous. The only time you'll see a jump, and we had it in our example here, is when you end up having a concentrated twist. Now again, that concentrated twist can be out in the middle, or it could be at the end. When you think about a beam like so, a built-in beam, again, think about your free body diagram. Force, 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 moment. So you're going to have a concentrated twist at the end of that particular one because there is a concentrated twist created by the support force. Okay, it should be 0 at pins, rollers, and free ends, because there's nothing there saying I'm going to stop you from rotating. Those pins, rollers, free ends basically rotate. Except provided there's no concentrated moment or couple. So there might be a twist applied to the end there, a concentrated twist. Well, you got to account for that, so we'll see that not being 0 at that particular end. Now, a lot of your moment diagrams are going to be parabolic because most beams basically are supporting some sort of uniform load. So if we have it in that form there, going back to your mathematics approach there, when you draw the shape, that's going to be important too. You'll lose points if you draw the shape wrong. If it's negative, then what you've got is a thing that's a positive moment, basically going over the hump and that sort of thing. If the coefficient in front of the x squared term is positive, basically then we've got a moment diagram that's shaped like that. Don't you just love these warm days? Question?
So, on the pictures of the diagrams that you drew, those are like depending on where you cut it, right?
Mm-hmm.
Like it's not just like the whole thing.
Right, right.
Always changing that way.
It's only valid, yeah, those equations are only valid for that little range that we give it. Okay? And one final point. Is we'll be looking for a min or a max of a parabolic or even a cubic at the point basically where the slope goes to 0, or as we saw looking at the equations, it's basically where the shear goes to 0. So when you draw your shear diagram and it goes through 0, okay, that implies then basically the slope is changing. We'll see why that is on Thursday. Hmm? Oh, it's Thursday, isn't it? God, it's been a long week. Yes, Thursday. Thank you. And let me know if I forgot my X. I seem to be forgetting my X's everywhere. Okay, we're going to... It didn't come out right, did it? My wife would not be very happy with that expression. Questions? Yes. That'll be on the test. Let's look at another example. We'll just get started on this. It's just one of these ones that kind of goes through these points that I just got done telling you about. Millimeters. Sorry, I'm trying to do mechanical problem here, something small. Okay, so we've got a problem like this, and we're going to be asked to draw shear and moment diagrams for it. The key thing is then we want to think about that, and that's why I keep saying think about it in terms of its free body diagram. What we're going to now do is substitute what those support forces are providing. So again, what I do is I substitute in what I have for a pin. I usually substitute it in terms of two components. It's an unknown force, unknown direction, or we substitute the two components of that particular force. By is a roller, so we already know its direction. It's only going to be in that direction. And then I got my concentrated couple at the end there. Now the first thing I need to do is then start solving for those end forces. So we do my equilibrium equations. Okay, so we know sum of forces in the x direction, AX is not going to contribute. And we'll pick a point where there is one of my unknowns there. So I'll take the moment at A. So my By is 2 millimeters away. My twist is basically going to be in the positive sense there, so I showed it's positive. And then the only other thing that's happening to the moment equation is that 120 Newton times millimeters. So again, it's showing up as that free vector there. It's already in component form for moment. And when I got done, basically, we find that By is equal to 60 newtons acting up. Exactly. So we won't even go through the equation. We know in terms of vertical equilibrium, it has to be that way. But again, the trick is then drawing my moment and shear diagrams. How are we doing on time there? We've got 5 minutes. So again, my AY now is going to be 60 this way, and this will be 60 this way. Okay, again, summing forces in the y direction, what we're going to find then is my shear because they're both pointing down, right? So one's got to go the other way to keep it in equilibrium. And then moment and then it's going to vary by its moment arm there. Okay, so my moment diagram my free body diagram for the second piece there, the cut in this section, is now going past the support B. And the point I want to make here is now notice, don't think about it in terms of the support, but think about it in terms of that concentrated force. When I consider my equilibrium equation, B is now equal to 0. So I'm going to see a change in my moment diagram there, or in my shear diagram. I draw my moment diagram. I've got 60 at x, which I haven't put on there. I am forgetting my x's again. So that's 60x and then 60x minus 2. Now notice the 60x pieces fall out, and what I end up with is a constant moment. I'm hurrying. Okay, my free body diagram looks like so. My shear diagram looks like that. So if there's only shear in this portion here, nothing in that portion, Stop it.
Now it's just revenge.
Yeah. Vicious. Boy, I let you guys run you a minute too long and you go crazy. So the moment diagram, as we saw, changes by that x. And then once it gets here, that couple kicks in. Now it's a fixed couple, right? So when we get past that, then it's going to stay the same. And again, we see a jump now at the free end of 120 because there is that concentrated twist at the end. So that's where I wanted to show you that. Have a good weekend.